In this first of a series of videos on motion, we are going to look at the basic concepts of motion, and we are going to derive certain fundamental equations of motion that we are going to use in more complicated motion problems later on in the course. So the study of motion is often referred to as kinematics. The Greek word kine or kaini means to move, it's motion. If we think of the term biokineticist, it's someone who studies the motion of the human body. Now, motion implies movement, and so we are going to define motion very simply as the change in position. Is the change in position of an object with respect to a reference point. So it's very important to note that motion is relative to a frame of reference. So for instance, if you and I are both sitting in a motor car that is moving, we are not moving with respect to each other, but we are both moving with respect to someone standing at a bus stop on the side of the road. So motion is the change in position of an object with respect to a reference point. So that is an important definition. Now, we have already looked at certain concepts which I'm going to briefly review. So the first is distance. So if we have an object, let's say for instance a person is walking from point A to point B, and that distance is 100 meters. And let's assume that the direction in which they are walking is the easterly direction. So we are going to just put a little compass here, north, east, southwest. So they've walked in 100 meters in an easterly direction. Then at that point, they decide to walk 50 meters in a southerly direction to point C. And once they've arrived at point C, they then decide to walk in a westerly direction 100 meters in a westerly direction. This was in a southerly direction to come to point D, which if you look at the diagram shows us that D should lie directly south of A. So now if we ask what is the total distance, then we must refer back to the definition of distance, and that is that the distance is the length of the actual path traveled by the object, in this case the person. So the length of the actual path traveled would be from A to B is 100 meters, from B to C is 50 meters, and from C to D was another 100 meters. So the total distance would be 250 meters, and recall that distance is a scalar, so there's no direction associated with it. To determine the displacement or the change in position, we draw a straight line vector from the start position to the end position of the person's journey, and we represent this with delta x. Remember, the displacement is a vector quantity. The delta stands for change, the x for position. We place an arrow on the top to denote it's a vector. And so if we look at the geometry of this problem, this is in actual fact a rectangle, and delta x is the opposite side of a rectangle, so delta x is going to also be 50 meters. And the direction of delta x is going to be from A to D, which is in the southerly direction. So we need to specify the direction, so this would be 50 meters south. So these two quantities are sometimes confused because if the object is moving only in a straight line, then the magnitude of the distance and the magnitude of the displacement will be the same. For instance, in walking from A to B, the distance is 100 meters, and the displacement, in other words, the straight line length between where the person starts at A and ends at B, is also 100 meters, but being a vector, displacement would have east associated with it. But as soon as the person changes direction, then the distance and the displacement differ. So this becomes very important when we look at determining the speed and the velocity of an object. So if we now assume that the total time that it took for this person to walk from A to B to C to D is 40 seconds, we then are able to work out the speed and the velocity. Now, earlier in the year we learned that speed is the total distance traveled per unit time, so that would be t total. So that would be 250 meters over 40 seconds, which equals 6,25 meters per second. This is the average speed, so we put a line or a bar on top of the quantity, because in walking from A to B to C to D, it's highly unlikely that the person would be walking at the same speed all the time. He would start maybe at rest, then speed up, then slow down, then change direction, speed up, slow down, change direction, speed up, and then slow down and come to a standstill. So this is the average speed, which is if he were to walk at that speed for 40 seconds, he would cover the same distance as the person walking the way that they did. If we are now to work out the velocity, then referring to the definition of velocity as being the rate of change of the position of the object per unit time, and velocity is a vector because the change in position is a vector, then this would be 50 meters south in 40 seconds. And so the velocity would be 1,25 meters per second south. This too is an average velocity, so we put the bar on top. The next quantity we need to look at is that of acceleration. Now, acceleration is defined as the rate of change of velocity. Now, when we talk about rate of change, we are referring to how that particular quantity changes. So we represent that as delta V. And rate in kinematics refers to change with respect to a change in time. So acceleration, which is a vector quantity because velocity is a vector quantity, can be described mathematically as the change in velocity per unit change in time. That delta t would be the time interval. So if we consider an object that is initially at rest, and I'm going to use VI, I for initial, to represent the initial velocity, 0 meters per second. And then this object is moved in such a way that 5 seconds later, the same object is traveling at a final velocity of 10 meters per second. And because we're dealing with vector quantities, we are going to refer to direction. So let's say to the right is north and to the left is south. And let's suppose that the time interval that within which this change in velocity takes place is represented by delta t, and that is 5 seconds. And we assume that this change in velocity is uniform, and that's an important term. That's a uniform change in velocity. What that means is that the change per unit time is the same throughout, so there's no sudden jerks. It's done in a consistent manner. Then we can work out the acceleration. So the acceleration is the change in velocity over the change in time. In physics, a change is always the final quantity minus the initial quantity. So in this case, it's V final minus V initial. Note that I keep the arrow on the top purely for me to keep in mind that this is a vector quantity. This is especially important when there is a change in the direction of the object, as this results in a sign change for the velocities, or for the velocity. So now, working this out, we can see that if we define north as positive and south as negative, then we have a final velocity of plus 10 meters per second minus the initial velocity, which is 0 meters per second, over a time interval of 5 seconds. So the acceleration is going to be 10 meters per second over 5 seconds. 10 divided by 5 is 2 meters per second per second. Now, we need to neaten this up. So meters per second means dividing by seconds over 1. And if we divide a fraction by a fraction, we can tip and time. So this is meters per second times 1 over second, which is the same as saying meters times 1 is meter, second times second is second squared. Now, using laws of exponents, keeping in mind that k over x to the m is equal to kx to the minus m, when we take a power and move it across the division line, we change the sign of the exponent. We can also write this as meters times second to the minus 2, because in effect we're taking the second squared upstairs across the division line. So looking here now, we're not quite finished. Because acceleration is a vector quantity, we need to specify a direction. So this is 2 meters per second squared, or meters times second to the minus 2, in a northerly direction. And that would be the complete answer. In this video, I am going to introduce the graphical representation of motion simultaneously with the mathematical formulation or the mathematical description of motion. So graphing is a very powerful way of visualizing what is happening. So we're going to represent the velocity versus time on a graph. So the time axis is the horizontal axis, and we're going to make the velocity axis the vertical axis. So this is going to be a graph of v versus t. Now, in this particular problem, the object started off at rest. So on the vertical axis, the velocity was 0, when on the time axis it was 0. And then over a period of 5 seconds, so it's 1, 2, 3, 4, 5, the velocity increased from 0 to 10 meters per second. So this is going to be 2, 4, 6, 8, 10. So at 0 seconds, the velocity was 0 meters per second. I'm going to represent it with a dot and a circle around it. And at 5 seconds, the final velocity was 10 meters per second. So what happened in between here? Well, we've learned that acceleration is the change in velocity per unit time, and that for this system, this object, it changed its velocity 2 meters per second per second. So what that means is after 1 second, the velocity changed by 2 meters per second. So at 1 second, this object was traveling at 2 meters per second. And then in the next second, from 1 second to 2 seconds, in the next time interval of 1 second, the velocity changed from 2 to 2 plus 2, which is 4 meters per second. And in the next second, the velocity of the object would have increased by another 2 meters per second to 6 meters per second. And in the next second, from 3 to 4 seconds, the velocity would have increased from 6 to 8 meters per second. Now, we can see that there is a trend here, and the trend is a straight line, and that we can fit this data with a straight line. And when one sees a straight line like this, we know that this represents uniform acceleration. Now, one must be careful of the term uniform. Uniform means consistency or constancy, but one has to be very well aware of what is constant here. So quite clearly, the velocity is not constant because the velocity is consistently increasing, but it's increasing at 2 meters per second per second. So the rate of change of the velocity is constant. And that is why we get a straight line. Because with a straight line, there is a gradient. And so if we look, let's say this is point X, and let's take this point here to be point Y, then the motion between the points X and Y of the motion of the object, there is a time interval of 1, 2, 3 seconds. So the time interval is 4 seconds minus 1 second, which is 3 seconds. And the change in velocity is from 2 meters per second at X to 8 meters per second at Y. So that's 8 minus 2 is 6 meters per second. So using the fact that gradient is rise over run, and the rise is the change in V, that's the rise, and that's the run between X and Y. The rise is 6 meters per second, the run is 3 seconds, and 6 divided by 3 is 2, and meters per second is meters per second squared. But this is the acceleration. This is just A. And so if we had chosen 2 different points, let's say for instance we had chosen point P and point Q to be those 2 points, and we had worked out the rise over run between those 2 points, we would get exactly the same value. And that's because of the fact that the acceleration is uniform. And straight lines have consistent or constant gradients, because we've learned that y equals mx plus c for a straight line. And in this case, the m, the gradient, is the acceleration. And the y-intercept is 0. As you can see that it's there. And the x, or the independent variable, is in actual fact time. And the dependent variable is in actual fact velocity. So at this stage we could rewrite this as v equals at plus 0. So from this graph we can now extract some really important information. So we've seen that the acceleration is equal to the gradient of that graph, and we know that, as we learnt up there, that the gradient is the change in the velocity with respect to the change in time. So that is the gradient of the graph. Now, if we replace the change in velocity with V final minus V initial over delta t, then we get another expression for the gradient and the acceleration. And now if I multiply delta t on both sides, so if I do this, and I multiply by delta t on both sides, which we're entitled to do, then we see that mathematically speaking, the delta t over delta t cancels to 1. And this now gives us an expression that looks like this. If I now take the minus V initial to the other side by adding V initial on both sides, then I get V final equaling V initial plus a delta t. Now, this is one of the standard equations of motion that we will be using to solve problems later on in this module. The next thing we're going to consider is working out the change in position of this object as it moves along its path. And what we're going to do is we are going to determine how far the object is from its original position, where if we call this original position x equals 0 meters, we are going to consider how many meters from that position the object is at 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. We're going to do this by looking at the area under the velocity time graph. So if we look at the change in position of the object between 0 seconds and 1 second, then if we look at the area under that graph, we'll see that in actual fact it is a triangle. And that triangle is a strange triangle. It's not a physical triangle with lengths of in meters or centimeters or millimeters, with an area in square centimeters or square meters or square millimeters, but rather the base is a time, 1 second, and the height is a velocity 2 meters per second. So the area of a triangle is half base times height. So this is going to be a half, the base is 1 second. The height is 2 meters per second. And a half times 1 times 2 is just 1. And notice that the seconds times meters per second gives us a unit in meters. So that's an indication that the area under a velocity time graph actually gives us the change in position of the object up to that point. What I would like you to do now is to determine the total change in position for the object at 2 seconds, at 3 seconds, at 4 seconds, and at 5 seconds, please. So whilst you're doing that, please pause the video. So now, looking at the calculations for the displacement of the object along its path at 2 seconds, the area that we are looking at is the area under this section of the graph, has a base of 2 seconds and a height of 4 meters per second. So the area would be half the base, half 2 seconds, times the perpendicular height of 4 meters per second, and a half times 2 is 1, times 4 is 4, seconds times meters per second is meters. Doing the calculations for the position at 3 seconds is a half the base of 3 seconds times the height of 6, and that gives us 9 meters. For 4 seconds, half 4 seconds times 8 meters per second gives us 16 meters. And for the full 5 seconds, a half times 5 times 10 gives us 25 meters. Now I want to draw your attention to the units. Under normal circumstances, if you calculated the area of a triangle, it would be, let's say in centimeters and centimeters, it would be a unit of centimeters squared. And sometimes learners get mixed up here is they work out the area, the magnitude of the area correctly, but unfortunately they go back to old habits and they put a square in there. This is seconds times meters per second, which gives us meters, and it should give us meters because the area under a velocity time graph gives us the displacement of the object, or the change in position. So what I would like you to do next is to plot the position versus time graph for this object's motion, and I'm going to ask that you pause the video again in order to do that. So I have represented our calculations in a little table on the right hand side here. And now I'm going to plot position versus time, or change in position versus time. So it's 0 seconds. The object actually had obviously not changed position yet. Then after 1 second, it had covered 1 meter. After 2 seconds, it had covered 4 meters. At 3 seconds, it covered 9 meters. At 4 seconds, it had covered 16 meters. At 5 seconds, it covered 25 meters. Now, looking at this data, it should be clear that you can't fit this data with a straight line, because if I draw a straight line through it like that, you'll see that there are a lot of data points that are far off the line. So it's going to be better for us to rather fit this data with a curve that looks like this. And this curve is in actual fact a parabola, which we'll learn more about in the next lesson. In this example, we are going to practice that which we've covered thus far in the video. So we are going to consider an object that is already traveling at an initial velocity of 4 meters per second in, let's say, an easterly direction. Our sign convention is going to be positive to the east and negative to the west. So the initial velocity is 4 meters per second, and that position there is obviously x equals 0. And what it does now is it travels for 8 seconds and reaches a velocity of 28 meters per second. in the same direction, so it's positive, and that the change in position is unknown. You will have to work that out. The time here is 8 seconds, and we set the time as 0 seconds here. Now, the challenge is that we'd like you to sketch, firstly, a velocity versus time graph. Then, using that graph, we'd like you to determine the acceleration, which I'm going to represent by A, and I will tell you that it's a uniform acceleration. And then thirdly, I would like you to sketch the displacement or change in position versus time graph for the full 8 seconds of motion. And then from that, you will be able to determine the total change in position of the object after 8 seconds. Lastly, I would like you to sketch the acceleration versus time graph, which we've yet to do, but it's really not difficult. And if you can do this, then it is a very good indication that you have mastered the basic concepts of motion that I've introduced in this video.